This is the third lecture of the fourth week, and we're going to discuss least squares assumptions focusing on multicollinearity. So there are four assumptions for the multiple regression. Assumptions 1 through 3 are overlap or the same as the simple linear regression. The last assumption regarding multicollinearity is the one that's only applicable for multiple regression. So we're going to focus most of our time on the last assumption. So the first assumption is that the conditional mean of u given x's is equal to 0. This interpretation is same as in simple linear regression. We had the same assumption, but instead of having multiple x's, we only had one x or one independent variable in the case of simple linear regression. If this condition fails, then it can lead to omitted variable bias. So we said that if a factor is omitted, but it still affects the dependent variable y, and if this omitted factor is correlated with one of the regressors x, then we have a situation where this assumption 1 fails because omitted variable u is correlated with x, which means that expected value or conditional mean of u given x is not equal to 0. So this condition fails, and this leads to omitted variable bias. In the case when you have an omitted variable bias, one of the solutions is to include the omitted variable in the regression as one of the independent variables. A second solution is to include a variable that controls for the omitted variable, and we'll discuss this further in chapter 7. This first condition or first assumption is satisfied when x's are randomly assigned. So in our case of looking at the test score and student-teacher ratio, if student-teacher ratio was randomly assigned across different districts, then the first assumption would have been met. So like in simple linear regression, the second assumption says that all of the observation needs to be identically and independently distributed. And this first or second assumption is satisfied when the data are collected by simple random sampling. The third assumption says that the large outliers are rare. In simple linear regression, we showed that one large outlier can impact the estimate of beta 1, or our slope coefficient. So because your regression model can be sensitive to outliers, it's important for you to check the data first, for instance, by looking at the scatter plot and making sure that there are no crazy outliers due to typos and coding errors. So the last assumption that is unique to multiple linear regression is that there is no perfect multicollinearity. And what do we mean by perfect multicollinearity? That's when one of the regressor is an exact linear function of the other regressors. So let's suppose that you accidentally include student-teacher ratio twice in your regression model. When you do that in Stata would drop one of the independent variables because Stata recognizes that there's a perfect multicollinearity, so it drops one of the variables. In some other softwares, it may just give you an error message. Let me give you some examples of perfect multicollinearity. So say we want to include both the percentage of English learners and fraction of English learners. So the percentage of English learner is just a fraction of English learners times 100. So the fraction of English learner would be 1/2 times 100 would be 50% of English learners. In this case, the percentage of English learner is a linear function of fraction of English learners. And that's why we have a perfect multicollinearity. Let's go back to how we can interpret the coefficient in multiple linear regression. So in our case, we had percent English learners and fraction of English learners in the model. The way we interpret beta 1 was how much the test score changes when percent English learner changes by a certain amount, holding the other regressor constant. So in this case, the other regressor is fraction of English learner constant. However, this doesn't really make sense because percentage of English learner and fraction of English learners are correlated, so they are moving at the same time in the same direction. So you cannot really measure how much the test score changes when percentage of English learner changes holding fraction of English learner constant, because if you change one, then the other would change too. So it's impossible to change one and not the other. The second example is when you have two different dummies that are moving in opposite direction. So let's say that there are two dummies, D and B. D is equal to 1 when student-teacher ratio is less than 20, and then 0 otherwise. And the dummy B is equal to 1 when student-teacher ratio is greater than 20. So you can write this in mathematical formula of B is equal to 1 minus D. So in this case, one dummy variable B is perfectly correlated with D because they are moving in complete opposite direction. So when D is equal to 1, B is equal to 0, and when D is equal to 0, B is equal to 1. So in this case, you have a perfect multicollinearity. The last case is when regressors are linear functions, or the regressors are linear functions of the intercept. So let's think about the intercept a little differently than we have been thinking about. So we normally write intercept as just beta 0 without any regressor. But we can think of a case as regressor x0i is with the intercept beta 0, and this regressor just equals 1 in every single observation. So let's say that you have a set of multiple dummy variables which are mutually exclusive and exhaustive, meaning that there are multiple categories and every observation falls into one and only one category. In this case, we're going to use an example of rural, suburban, and urban dummies. So in the case of measuring a test score, we're going to say each district either falls into rural, or suburban, or urban area. In this case, we're also going to assume that beta 0, the intercept, has a regressor x0i, which equals 1 in all observations. So if you include all of these dummy variables and the intercept or constant, beta 0, then you have a multicollinearity. And the reason why you have a multicollinearity is because of this function. So basically, the regressor of intercept x0i is equal to 1, and all of the dummies always equal to 1. So when you have a district that is rural, you're going to have 1 for rural and 0 for suburban and urban. When you have a district that is suburban, then you're going to have 0 for rural and 1 for suburban and 0 for urban. So no matter which observation you have, the sum of all of it would always equal to 1, which is the regressor of the intercept. So basically, you have a perfect multicollinearity. One of the solutions in the case like this is to drop one of the dummy variables, and this is the most common way of solving this problem. So you include the intercept, but say you drop the category or dummy variable rural. In this case, the way you interpret the coefficient beta 2 is that this is the average test score difference between suburban and rural area, holding the other variables constant. A second solution is, instead of omitting the rural, now you drop the intercept. So you run the test score on, you regress test score on rural, suburban, and urban. In this case, the meaning of coefficient beta 2 now is that it's the average test score of suburban, because when you have a district that is from the suburb, your rural dummy variable would equal 0, and the suburban dummy variable would equal 1, and urban dummy variable equals 0. So what you have remaining is only the beta 2. So beta 2 becomes the average test score of the suburban district. So in the case of perfect multicollinearity, it usually reflects a mistake in definition of regressors or some issues with the data. When you have perfect multicollinearity, your statistical software such as Stata will let you know either by giving you an error or dropping one of the variable that is perfectly collinear. So the solution to this problem is to change your list of regressors by either dropping one of them or modifying the regressors so that you don't have perfect multicollinearity. So the next idea that we're going to discuss is imperfect multicollinearity. Imperfect multicollinearity happens when two or more regressors are highly correlated. It's different from perfect multicollinearity in a sense that the two regressors are moving at the same time, either the same direction or the opposite direction, but they're not exactly on the linear line. One of the examples of imperfect multicollinearity is when you have percentage of English learners and percentage of immigrants in the model. You can see that how these two variables are highly correlated. So when the percentage of immigrants increases, then the percentage of English learner would increase, but they're not going to increase 1-to-1. When you run the regression of test score on these two variables, the interpretation of beta 1, as we said before, is how much test score changes when the percentage of English learner changes, holding the percentage of immigrant constants. But because these two variables are highly correlated, once you fix the percentage of immigrant, then percentage of English learner won't vary as much. So you don't have as much information about what happens to changes in percent English learners. One of the problems or one of the consequences of imperfect multicollinearity is that you're going to have a large standard error for one or more of the coefficients. So in this case, either percentage of English learners or percentage of immigrants, either one of them or both of them will be imprecisely estimated. For mathematical proof on why this may be the case, you can look at the Stock and Watson, Chapter 6, Section 2.